Hey, and welcome. Today we're going to be talking about different number sets, and you do not need to be in Algebra 2 to enjoy this lesson. The first number set we're going to be talking about are the natural numbers, denoted as such. The natural numbers. The natural numbers are include every positive whole number. So 1, 2, 3, 4, 5, 6, 7, 8, all the way to positive infinity. And it does not include zero. The concept of zero in the ancient early human times, you had these two oxen, and then you got a third oxen, you would draw a third oxen. Well, let's say that, you would need to document how many oxen you had so that the pharaoh or whoever knew how to tax you. But let's say that the famine struck. You got one oxen, you sell that oxen. Now in your ledgers, there's no oxen. You're not going to denote zero. Back then, they didn't have a concept for zero. I think it's officially formalized in mathematics in India. I don't know the date, by someone named Brahmagupta. But that zero is included in the next set. The next set is the integers. The integers, you're probably wondering why Z. I think it's Zahlen. It's German for numbers. But the integers are all whole numbers, including zero, negative, positive. So an infinite number from negative, I like to denote the ... to, everything prior. -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, and so on and so forth, forever in both directions. And then, so far so good. Here's where things get a little weird. Make that zero better, sorry. Here's where things get a little weird. Rationals. The rationals include, it's an infinite set as well, but they include things like 4/7, -2, 0, 1, 3/17, 2, that's a variable, 2.778, and so on and so forth. Is an infinite set. It includes any number that can be expressed first. We're going to let A and B, they're going to be integers. This is notation. A and B are from the integer set. So A and B are integers. A rational number is a number that has a fraction of two integers, two whole numbers. And the reason why we denote it with that Q or a bold Q is for quotient or quotient. I don't know how to say it in Italian. Giuseppe Piano, I think, is the name. I don't know when, but came up with or formalized again the bold Q concept for a rational number, a integer divided by an integer. And as you can see, these are all integers divided by integers. 4 is an integer, 7 is an integer. 4 divided by 7, rational. -2, as y'all know, maybe, any number can be written divided by 1, because any number divided by 1 is just itself. So that is a rational. 0 can be divided by 1. 1 can be divided by 1. That's a rational by definition, integer divided by an integer. But 2.778, how is that rational? Well, let me show you. That is rational because 2.778 is over 1. And if we multiply this by 1, it won't change it. And 1,000 over 1,000 is really just 1. 1,000 divided by 1,000 is 1. And if I multiply this top, the numerator, by 1,000, I'll be left with 2,778 divided by 1,000, which again is rational. Integer divided by an integer. So, hopefully you guys are convinced, but let's move on to the next set. The next set is one that you're most familiar with because it covers, maybe not most familiar with, but it covers numbers that pop up. It's an all-inclusive set. And that is the set of real numbers. The set of real numbers, rational numbers, real numbers. Set of the reals includes the rationals. So the rationals include the integers. So it includes the rationals, and it also has irrationals like pi, e, the square root of a prime number, like root 2 or root 3 or root 5 or, so on and so forth, the irrationals. So the real is, and also you got the negative and positive versions of all of these. Positive and negative pi, positive and negative e, positive and negative root 2. Again, all inclusive. The reals are all inclusive. And then we're finally left with the final set that we're going to cover. The one that we are covering in class for Algebra 2, the set of the complex numbers. Complex numbers include all the reals and the imaginary numbers. And the imaginaries mixed with the reals. How would I denote that? Maybe like a function of like, if I was to informally, maybe something like that. But let's not do that. Let's not mess around. Those are just a few examples, but another example might include 2 plus 3i, 14i, negative I, and so on and so forth. So those are the separate fields. We will be using these complex numbers in quadratics to understand imaginary intersections. For example, when does y equal x squared plus 10 intersect the x-axis? Oh, that's not good. I'm going to give you guys a visualization for those of you guys who didn't immediately see the issue with my question. I guess I'll just shorthand it. Solve. Solve. So when this intersects the x-axis, so when y is equal to 0. Solve for when y is equal to 0. Now, for those of you guys who don't immediately see the issue, let me explain it to you visually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, that is my y-intercept. And then I'm going to have a parabola that looks like that. Now, visually, when does that parabola? I butchered it a little bit at the end, but where does that parabola intersect the x-axis? It's positively sloped. It intersects at y equals 10. That vertex right there, that vertex point, 0, 10, that is the minimum point. So when does this function intersect the x-axis? Well, let's solve it algebraically since we can't visualize it. 2 to one side, 2 to the other. I'm allowed to do that. That leaves me with negative 10 is equal to x squared. I take the square root of both sides to eliminate that, to counteract that squared. So I'll be left with what x is equal to, because the square root of x squared, that's just x. And the square root of negative 10 is the square root of 10 times the square root of negative 1, or the square root of 10 I. So algebraically, I guess technically, if you square that, well, let's just go through the process together. Let me prove it to you. If this is what x is equal to, x is equal to the square root of 10I, then x is also going to be equal to the negative of that. Let me show you why, by plugging it back in. So when I plug this back in, my x squared plus 10 has to equal 0. My x squared plus 10 has to equal 0. So let's plug in square root of 10 times I. And, well, I guess I could just keep it simple. I could just keep it square root of negative 10 squared. That just becomes negative 10 plus 10 is indeed 0. But what about negative square root of 10 I? What about negative? Let's see. Negative square root of negative 10 squared. Well, negative times a negative is a positive. The square root cancels out. So I'm left with negative 10 plus 10 again, which is 0. So algebraically, at least, this answer here would be the solution to this problem. And it would involve complex numbers. Okay, cheers. Thanks for tuning in. Bye.